Okay, welcome back. So we know now how to create data frames. Um, we know how to specify the label names if we want, or just use the defaults 0, 1, 2, 3, and so on. And we can add and remove columns, add and remove rows, access columns, access rows, and access individual cells within a column and a row. Next, we're going to take a look at how to do slicing and indexing within data frames. And to do this, I'm going to build myself a data frame based on a two-dimensional ND array. Alrighty, so we're going to say A12 is np.arange 12. Yep. Alright, so that's a one-dimensional ND array, but I can reshape that. A12.reshape as a 4 by 3 array. So now I've got 4 rows and 3 columns containing those values 0 through 11. And I can use that, in turn, as the data within a new data frame that I'm going to construct. Now here, in addition to specifying the index or the row labels, I'm also specifying column labels. Previously, when we created the data frame, we used a dictionary where the keys were used as column names. But this time, I'm not using a dictionary. I'm using a two-dimensional ND array for my data. Okay, so F2 is going to get pd.dataframe from a12.reshape 4 by 3. Let me just do that. Let's just start with that. And what we're going to see is that the default rows are sequential integers. Likewise, the default columns are just sequential integers. This is a data frame, but the row labels are 0, 1, 2, 3, and the column labels are 0, 1, 2. And that's, not very friendly to have as row and column names. So I will specify that I want my index to be, and I'm going to use very clever names here, R0, R1, and R2 for rows 0, 1, and 2. Additionally, I can specify the column names, and I use the keyword argument columns for this. Columns. Actually, I'm running out of space, so I'm going to delete that whole business there and type columns on the next line down. And once again, I'm using very clever names. C0, C1, and C2. And anybody see the mistake that I made? I've got 4 rows, not 3. So I better remember to have R3 up here as well. Fortunately, I didn't hit the enter key before I discovered that. And so now I have my my F2 data frame with named rows and named columns, although the names are not very imaginative. So far, so good. Alright, so I can access a column like we did before by saying F2 sub and the column name. I can access a row by saying F2.loc and the row name. Alright, so F2 sub C1 gives me the column C1, F2.loc sub R2 gives me the row R2. And I can get a Boolean index from a data frame, just like I can get a Boolean index from an end array. If I say f2 mod 3, now is equal to 0, that's going to give me back a true for each cell that's evenly divisible by 3, and a false otherwise. This thing is a data frame, but it's a data frame of Boolean values rather than a data frame of integer values. I can use that Boolean data frame as an index and say something like times gets 2. And what's going to happen is that I'm going to multiply each value by 2 where the Boolean index is true. If the Boolean index is false, those values are going to be left unaffected. All right, so f2 sub f2 mod 3 is 0 times gets 2. And f2 now contains, instead of 0, 3, 6, 9. Instead of 0, 3, 6, 9 in the first column, now we have 0, 6, 12, 18. So all those values in the first column have been doubled, but the sub 1 and sub 2 columns have not been modified. Okay, so this idea of Boolean indexing and scalar multiplication, these are exactly the same way in data frames that they are in two-dimensional ND arrays. Now, to access a slice of rows, here's my f2. I can say f2 sub r0 up to and including r2. You may remember when we talked about stock tickers that I said, well, if you have from Apple up to Cisco, unlike using integers, the final one is included in the slice. So here, I'm going to get R0, I'm going to get the row R0 included in the slice, and I'm going to get the row R2 included in the slice, and it would be helpful if I remembered to say .loc. Okay, since I'm trying to access rows, I've got to remember to say .loc, which I forget about 1 time out of 4. All right, so there I got my slice from row R0 up to and including row R2. If I say f2.loc 0:2, on the other hand, iloc, right. Thank you. Yep. Yeah, I can use integer subscripts, but I have to use iloc instead of loc. So I can say iloc 0:2. And now the meaning is from 0 up to, but not including 2. So I'm just going to get the first 2 rows from that data frame. Yeah?
Apart from small data frames whose headers and stuff we know the names of, because that's what you need the loc for. When else would we ever use loc? Like iloc is, we have positional based searches. So wherever
well, for example, if the labels are dates, it would be fairly. It's fairly common to have like transaction logs where the labels are dates, and then I mean you can easily find the beginning date and the end date and convert those to integer subscripts and use iloc, but you can just leave it as .loc as well. Okay, so loc uses labels and iloc uses ordinary integer values. Okay, I can use individual subscripts. I can use a slice of subscripts. And here I'm using so-called fancy indexing, which is going to allow me to change the order of some rows. All right, so F2 sub R1 gives me just the F2.loc. Maybe more than one time out of 4. F2.loc of R1 gives me that row. F2.loc of R2 colon R3 R1 colon R3 R2 gives me row 1 and 2. F2.loc, if I use the square brackets again, I can specify the this is what's called a fancy index, and I can specify that I want these rows in different orders, and I can even specify that I want them repeated. So if I say R3 comes first, R1 comes next, and then R3 comes third again, that's fine. I'm going to get my data frame that's displayed here is going to have a copy of R3 at the top, and then R1 as the second row, and then R3 again as the third row. None of these operations that I've been doing here have actually modified F2. F2 remains unchanged throughout this. So F2 still contains what it originally did. If I wanted to capture any of the results of these operations, I would need to create, a new variable name, like F2a gets F2.loc of R3, let's say. Okay, so F2 is unchanged by that, but I now have F2a containing the result of what I did. Okay, so again, this is basically like what we talked about last week with AND arrays. We can access individual items in the array, we can access slices in the array, and we can use fancy indexes in the array or Boolean indexes in the array to access various configurations of subsets of what's in the array. Here are examples using iloc. It's basically the same as loc, except that I'm using integer values instead of string labels. All right, so here's my F2. F2.iloc sub 3 is the last row. F2.iloc sub 0 colon 2 is just the first 2 rows. F2.iloc square bracket 1 1 1 1 is a data frame that has 4 copies of row R1. Questions? There's nothing really very exciting going on here, is there? Okay. So the examples that we've looked at on the last couple of slides have all been row-oriented examples. What about columns? What if we want to deal with columns? Well, to deal with columns, we just specify a comma and a second set of labels for the columns. Now, recall that if I have a data frame and I want to get a particular cell within the data frame, I can say f2.loc and then give the row label followed by the column label, and that works fine. So row comma column will access for me this cell containing the 8. If I wanted a slice of rows that's fine, and I can still specify which column I would like. All right, so this time I've specified a slice of rows, row R0, R1, and R2, but only column C1. Or I can specify, let's say, every row and a slice of columns, let's say. And I've got a typo in here. This comma shouldn't be there. Okay, so colon for the rows means every row, from row 0 up to and not including one beyond the end of the data frame. But I only want columns C0 and C1. Oh, I'm sorry. I don't use the square brackets. Okay. I was accidentally creating a fancy index there, which I didn't mean to do. So I just leave out those square brackets here. Sorry about that. Okay, so the rows are going to be all rows. The columns are going to be from C0 up to and including C1. All right, so I got all the rows, but just the first two columns of each of those. Now, I can do fancy indexing on the columns using the square brackets. So C0, comma, C0, comma, C2, comma, C2. And what I'm going to get is all the rows. I'm going to get C0 twice and C2 twice as my 4 columns. Okay, so as with ND arrays, we can do indexing and slicing and fancy indexing and Boolean indexing on the rows and or on the columns within our data frame. Questions? Okay. Okay, so here's where I mentioned missing values. This is a two-dimensional example instead of a one-dimensional example. I've got my F3 data set. I'm sorry, I've got my F2 data set, all right? And I'm going to make F3 be a copy of F2, and then I'm going to tinker with F3 a little bit. So F2 has 4 rows and 3 columns. I want F3 to have 3 rows and 4 columns. So instead of being 4 by 3, I want F3 to be 3 by 4. So I'm going to drop R1. Now that actually doesn't change F3. I have to say F3 gets F3.drop R1. Okay, so F3 now has the same columns as F2, but I've eliminated row R1. And now I'm also going to add a column, F3 sub C3 gets... Okay, I just noticed that on slide 37 I did these in the opposite order. I added the column and then I dropped the row. So here I've already eliminated row R1, and the values I need to add are going to be 1, 5, and 7. So 1, 5, 7. for the 3 rows. All right. So F2 is a 4 by 3. F3 is 3 by 4. They obviously have several rows and columns in common, but they also obviously are not the same. So if I try to add these things together, I get a situation similar to what I showed you before, but this time it's two-dimensional. I have not a numbers throughout row R1 because that doesn't even exist in the second data frame. And I have not a numbers in column C3 because that doesn't exist in the first data frame F2. I can use a fill value, as I showed you. However, this will only work for the cases where one data frame is missing a value or the other data frame is missing a value, but not both. If they're both missing a value, then even using a fill value is not going to work. Pandas are just going to say, wait a minute, I can't use a default value of 0 for both things. Both things are missing. They're they're not 0. So I'm going to leave it as not a number in that case. All right, so I will say F2.add F3 with a fill value of 0. And I do get the default value of 0 used in C3, where C3 is only in one of the data frames. And likewise, I get the fill value of 0 used in R1, where that row is missing from 1. But in this case where there is no cell, R1, C3, in either of the 2 data frames. And so at that point, Pandas just says, no, forget it. That's too far. I'm going to leave that as not a number. And you just have to deal with that in some other way. Now, the other way to deal with that is fairly straightforward. Let me say F2A is equal to the result of doing this add okay. Well, I can say F2A where F2A is equal to not a number. I'm probably going to have to say NP dot not a number equals 0. And that handles the case of replacing not a number with 0. Hello? F2A equals NP dot not a number. Oh, they're all false. Oh, yeah, that's right. I had forgotten. Not a number is not equal to anything, including itself. So if I say NP dot not a number and I compare that to NP dot not a number, that's false. So what I need to do instead is to say F2A dot is null. There we go. And say F2 sub F2A sub F2A dot is null equals 0, and I have now I've now got numbers in every cell in my two-dimensional array. And whether that's legitimate to replace missing data in 2 different data sets with a 0, well, if it's economics, it's probably okay. If it's a medical study, probably not so much. So it depends on the context, right? Let's see. Oh, you can sort data frames as long as the values do have a less than operation to sort them by. So let's see. All right, so I've got F2 with 3 columns and 4 rows, and I just want to create F4 as a data frame based on F2's data. Let me make sure that that's going to fly. F2.data. No, F2.data. No. Hey. Oh, I see, okay. All right, I can't directly extract, but I can just convert. I can convert the data frame back to an ND array, and that accomplishes the same thing. So if I say np.array F2, that just gives me the data within the data frame. So now I can say F4 is pd.dataframe np.array F2 with the rows named, and I'm going to do these out of order intentionally. So A, D, B, C. And the columns also out of order, Z, X, Y. Okay, so now to sort these rows and columns, I can say F4.sort index, and that sorts the rows in ascending order by the row label. So I should get rows A, B, C, D as a result. Now F4 isn't changed, but what I'm seeing is a copy of F4 with the rows sorted. Now, as an alternative, I can say F4.sort index, and here's a place where you feel like this wasn't really designed too well. Wouldn't it be nice if you could just say sort columns? No, sorry, you can't do that. You have to say F4.sort index, but axis of the sorting is equal to axis 1, which is the columns. And so now I have the columns X, Y, Z. All right, so the rows are considered to be axis 0. The columns are considered to be axis 1. And so you need to give that as an argument to the sort index. You can also do things in descending order rather than ascending order. And here again, you kind of wonder about the design. You can't just say, descending. You have to say ascending equals false, which seems a little silly. All right, so I'm going to say F4.sort index. Now that's sorting the rows, but I want the rows sorted in descending order rather than ascending order, so I have to say ascending equals false. And then I can also sort the index of that resulting data frame by columns by saying axis equals 1. All right, and so I've got the columns in ascending order and the rows in descending order. But again, none of this actually changed F4 directly. If I wanted to save that back in F4, I would have to say F4 gets that stuff. Make sense? Questions? Oh, okay. Summary statistics. How are we doing? Oh, we're doing great. I'm going to finish too early. NumPy, NumPy has a module called random that generates random numbers and of a variety of different distributions. All right, so I'm going to set the seed to 1. By doing that, I'm going to make sure that the values I get interactively are going to be identical to what I have in the notes. If you don't set the seed to 1, then the seed is set using the clock on your system, which means that unless you run your examples, well, okay. So actually, I was going to say that on Unix systems, it used to be that if you ran the program twice within the same second, the clocks would match, and so you wouldn't see any change. But now I believe that we're using the clock down to, like nanoseconds or something. So I doubt whether it's possible. I doubt whether it's possible to run the application twice within the same, time frame. All right, but I want to get the same values that I have in my notes, so I'm going to say A5 gets np.random.randn. Now randn means to give me draws from a standard normal distribution. So normal distribution with mean 0 and standard deviation 1. I specify the dimensions that I want. So if I want a 3 by 3 draw from those random numbers, I can say 3 by 3, and there are my random values drawn from a standard normal distribution. And you can see that these values, to within some round off, match the values that I have in my notes. Now, it's really hard to be able to tell the difference between two different numbers that have 8 digits after the decimal point. So we're not going to try. We're just going to keep track of 3 digits. Let me set my seed to 1 again to make sure that I'm starting over. And this time we'll say F5 gets numbers drawn from a standard normal distribution, but let me round these to only 3 digits. And now A5 does look exactly like what I have on slide 42. Okay, so I've got a 3 by 3 array of numbers drawn from a standard normal distribution, but only out to 3 decimal places. And from that, I'm going to create my data frame. Now, I'm a remarkably bad typist, especially when people are watching. And, I guess I'm doing okay here. I was going to, well, I'm going to do it anyway. I was going to use a comprehension for one of these lists, and I'll do that for columns. So for columns, I'm going to say I want a list of C appended with the stir value of I for I in range 3. So peculiarly, even though that's more typing, for me it's easier to type than quote C0, quote, comma, quote, RC1, quote. And what's happening here is that in this comprehension, I'm getting the character C appended by the I'm getting the string C appended by the string representation of the number 0, 1, or 2. And I'm doing that for I going in 0, 1, or 2. And so that will give me the correct column names. And now I have F5 with the values I want and the row and the column names that I want. Good so far? All right. Okay, and I can get all kinds of convenient summary statistics out of this. I can say F5.sum. Okay, sum is predefined for data frames. I can say F5.mean, F5.min, F5.max, f5 dot variance, f5 dot std. So std is sort of the unfortunate name of the standard deviation function. Usually it's stdev or something. But this is going to be our standard deviation for the rows in this data set. Okay, so I've got sum, mean, variance, min, max, median, a whole bunch of other functions I can use. I wanted to show one here. What did I forget? F5 dot. Oh, yeah. Describe. All right, descriptive statistics. F5 dot describe. Just gives you descriptive statistics of your overall data set. Okay, telling you how many records there are, what the mean is, what the standard deviation, what the minimum is, and this is on a column by column basis. We also get quartiles here. So we get the quartile values, 25, 50, and 75, as well as the max. There is a lot more to know about statistical analysis in both NumPy and data frames. You can also do linear algebra kinds of operations in NumPy and data frames and so on. Well, that's the end. Anybody have any questions about anything? Okay.